Today we're looking at volumes of rotation, and I think you're going to really enjoy this lesson because it brings together two things that you already know well: the area underneath curves, which we can find by integrating, and the volume of a cylinder. So let's just start with something we already know. We can find the area underneath any curve bounded by the lines x equals a and x equals b just by integrating y with respect to x. So then imagine what would happen if we took that area and we rotated it around the x-axis over and over again. What we're going to get is some sort of 3D shape that's actually got volume to it now, and we're going to be able to find that volume really quite easily. Now, this is somewhat reminiscent of what you'd get if you were perhaps turning wood on a lathe. You might have seen people put a block of wood onto a lathe that spins around and around, and then they can use a chisel, and by moving along like this, they can carve out a shape like this. What will you get if you take a slice anywhere in that shape? Well, you'll actually get a perfect circle, won't you? And the size of that circle will vary depending on how far along and what, in fact, your function of x is. You might also like to imagine that you're doing pottery and you've got a pottery wheel that's going around and around, and by moving your hand in one particular place, you're going to be able to change the shape of the entire bowl or whatever it is that you're making. Now, thinking about how we found area in the very beginning here when we're learning to integrate, remember we carved it up into a whole series of little rectangles, and we said that if we could find the area of each rectangle and add those areas together, then we'd be able to approximate the area underneath that whole curve. Now, how wide were those rectangles? Do you remember? We said that they would be a small change in x wide because we wanted to make them as thin as possible, infinitely thin. And that's where we got that notation dx, because delta x is sort of stylized into dx. So each rectangle was dx thin, and each rectangle was y tall. And that's why when we found the area of the rectangles, we wanted to sum them up, and this notation means take the sum, from b all the way up to a. Actually, that should say a up to b, shouldn't it? And we want to find the base, which is dx, times the height, because that's the area of a rectangle. So that was quite straightforward. This should help us here because really we need to now sum the volume of a whole lot of little slices of this shape. So the slice of each slice, we could just take the slice in the middle here, and I've drawn this one over on the side, and I've given it an edge that's a different color there so that we can see that it does actually have some thickness. If we look at each slice, it's actually just a little cylinder, isn't it? And drawing it this way around, we can see that the height here would actually be the radius of that circle, which is not r for radius, but it's actually y, because that height comes from whatever the y value is on our function. And then how thick is our cylinder? Well, the same as over here, it's dx thick. So then the formula for the volume of a cylinder is pi r squared h. So for us, we'll have not pi r squared, but pi y squared. That will give us the area of each of these slices. But to give it volume, we need to multiply by the height of the cylinder, which is just the width of it there, which is dx. Now that is the formula for the volume of one slice, but we want to add together all the slices from A up to B, and that is really, I think, quite straightforward. That gives us the formula for the volume of this shape. Really quite similar to this one, except pi is involved, and we need to find y squared for obvious reasons. In this example, we've got a nice simple function to sketch. So that's just a straight line with a gradient of 2 going through the origin, something like that. And we need to find the volume of the solid generated by rotating this around the x-axis from x equals 0 up to x equals 5. So first thing to do is to think through when x equals 5, y is going to equal 10. Let's put y here and x down there. So we've got an area that looks like this going around and round. Now, clearly when we rotate this around the x-axis, what we're going to get is a perfect cone. So they've asked us to verify our solution using the formula for the volume of a cone. All right, so first step, write our formula. We need 0 to 5 pi y squared dx. Now, you've got a choice in every single one of these questions. If you want, you can bring pi outside the integral, completely up to you. Advantage of bringing it out is that it's clear of the integral and your integrand is easier to integrate. Disadvantage is that you'll need to put pi and then put brackets, and when you do your subtracting, you'll need to make sure that you multiply everything by pi. I might do it that way this time to show you, and you can take your pick every time you do these questions. Okay, next step is that you need to actually integrate with respect to x. Now, that means that you've got to have something here that's got x's in it. So if y is equal to 2x, y squared is 4x squared. So that's a key first step, is to make that change. Now we can go ahead and integrate it, and we'll get 4x cubed over 3, and write our bounds in like that. And on the next line, we'll have pi multiplied by 125 times 4, which is 500 over 3, minus 0. Now, when you go to give your answer, we could write 500 pi on 3. We could work out exactly what it is. The question will tend to ask you to round off to a certain number of decimal places or to leave your answer in exact form. So this is exact form and it's volume, so we need cubic units on it. Now, let's verify this with the volume of a cone. Now, that formula is 1/3 pi r squared h. In other words, 1/3 of the volume of the cylinder that it sits inside perfectly. So if we consider here, our r is going to be 10 because the base, we've got a cone on the side. So we're going to have 1/3 times pi times 10 squared multiplied by the height of the cone, which is 5. And sure enough, that will give us the exact same answer as we had down here. In the next example, we've got a shaded region defined by this semicircle and the line x equals 2, and it's rotated around the x-axis, and we need to find the volume generated. So picture the shape that you're going to get and then launch into your formula. We need to find from 2 up to 4 y squared dx. Oh, sorry, pi y squared dx, I should say. Now, writing the formula this way every time is handy because you're thinking, okay, I need the area of the circle multiplied by its width, and the formula's making sense to you rather than you memorizing it. On the next line, I think bring the pi out the front, we keep our bounds, and we think about what y squared is, and in this case, squaring both sides, y squared is just 16 minus x squared dx. So you've got the basic idea of the formula, and then you've got the formula that you need to work with for this specific example. Next, we need to integrate both terms one term at a time. So we'll get 16x minus x cubed on 3. And we'll put our bounds in like that. Next, we need to sub in our bounds. Now, be careful here. There's going to be 2 parts, and we've got 2 things to sub in. So we sort of need big brackets that will allow the pi to be multiplied by everything we get in here. Now we're going to have 16 fours minus 64 thirds minus, and now I'm going to use my normal brackets in here for the next 2 terms. See what I mean here? We don't want to make a sign error in here, and we've still got to multiply all of that by pi. So subbing in my 2 now, I've got 32 minus 8 thirds. So now tidying up what's in here and leaving the pi out of it still, I've got 64 minus 32, and I've got negative 64 thirds plus 8 thirds, so that gives me, what's that, minus 56 thirds. Now you might choose to put all of this in your calculator and just leave the pi out and put that in at the end, or you could do part of it in your head and reach for the calculator for part of it. Once you get to here, your calculator will tell you that this part is 40 thirds, so you can write it as 40 thirds pi or 40 pi on 3, and don't forget units, which need to be cubed units.